for interactive interaction with humans in these environments. And and so some contexts you might think of is of course light control. So if people come into the room, maybe we want to switch on the lights. If room occupancy, so kind of sensing this, and for switching on the lights, there would be maybe some activities about, let's say, daily activities. So what people are doing over the day, that could be activities like kitchen activities, reading activities. So just basically learn about the activities which are conducted in this environment, and then react accordingly. Okay, and this relates to kind of the technology all of you are using nowadays, and I think you're very familiar with, which is location-based technology. And this has been, if you remember a couple of years back, this has been kind of a novel, innovative, and also kind of a technology which helped the establishing of new services and even of new businesses. So if you can rely on location-based services, you can actually build a business around it, and that's what's happening now all over the world. So what we would like to do is to develop ambient intelligence in such a way that it also becomes usable, similar to these location-based services, but more, let's say, for spaces. So you would have a service which you can program into an intelligent space to maybe monetize that service. And we're not yet there, and but that's kind of the scenario we have in mind. And just as a first kind of a motivation, and also to show what is possible, I have a video here which is from my group. So you see on the video there's Darius Salami. He is basically operating a radar. So we see the radar here on the left side of the video on the tripod. And what you see on the black screen, this is what the radar is seeing. So basically, there's a cloud of points, and you see that's somehow moving. And what we are doing is that we interpret these cloud of points for gestures. So kind of this radar is transmitting chirps, so basically signals out. These are reflected from objects in the environment, and then basically these reflections we see here, these reflections generate these cloud of points, and that is then interpreted for gestures. And what we do here, you see the slide set on the right side. So Darius is actually giving a presentation, and he's controlling the advancement of the slides via his gestures. So there's kind of, okay, we just saw it again. So you can do his gestures, basically control how the slides are advanced or going back. Okay, this just as a motivation. So this is in principle what we have been working on for quite a couple of years now, and this is what I mean with the kind of technology which is contact free, right? So we can do sensing, but we don't need a contact for this sensing. Yeah, and I wanted to, that we also get a little bit technical. I wanted to first explain how this is possible. So we saw the video on the previous slide. We saw these cloud of points in the screen, and just that we are on the same page, I wanted to briefly explain how this works technically. So basically we are for frequency modulated continuous wave, and so this radar operates, as we see here, in a region of 76 to 81 gigahertz, and so we have a 4 gigahertz bandwidth, and kind of this frequency modulated continuous wave. The meaning is that we see this here. Basically, the radar is sending out a signal. We call the signal chirp, which is starting at the lower frequency and then linear increases in frequency. So this is what you see here over time, right? Over time, we first start with the low frequency, and then the frequency gets higher and higher. So of course, this is only kind of a time span relative to frequency would normally be longer, but this is basically how it works. And when we look at this in the frequency domain, so this is what you can see here. So in the frequency domain, we see that, okay, we started here, the 77 gigahertz, and basically linearly increase the frequency until we reach the maximum. And from here, basically now the next chirp would start. So then basically we would repeat the same thing again. So what happens now when the signal is sent out? So imagine that we have an object, so we can see this here. So we have the radar who send out the signal, and there's some object in the environment, and of course this object causes a reflection, right? So we have a reflection of the signal coming back, and so now this is the red signal here, right? So we send out the black one, and then because there was some reflecting object, we get back the red signal here, this red line. It's basically when we assume that the object is not moving, which is kind of a realistic assumption in the sense that because the movement of objects in the environment is typically so much slower than the time of this chirp here, that we can assume that the other objects are basically static for the duration of the chirp. So we have a static reflection here, and it's basically just a copy, if you want, of this what we sent out. It's coming back. So we see that there's some time difference here between sending out and receiving, but otherwise it's the same kind of signal. So what we do then, the sensing, and please bear with me, we come to how to do the sensing in a second. We have the send out signal, we have the signal which we receive at the same time, and then we take the difference between the sent out and the received signal. So what happens? So we see it's the same signal, it's just delayed in time, right? So basically we see here is an offset. So basically at the same time, we are sending at one frequency and we receive at a lower frequency. If we take a difference there, that means the resulting signal, which is the intermediate frequency signal, it will be, when we plot this in frequency domain here, it will be a constant frequency kind of a signal, right? We see that the blue signal here is kind of constant in frequency, and this kind of represents one obstacle in the environment. So one thing we can see is that basically the distance to the obstacle is directly correlated to the time of flight, right? So the sending out the signal and receiving a signal back. So basically the time it takes relates to the distance. So kind of this, how far this is off here, right? With these two signals, that relates to the distance to the object. So we can basically now, for this intermediate frequency, we can say at which frequency, so how high we have this here at the frequency domain, this tells us how far the object is away. Yeah, this is for one object. If we have two objects, we get multiple of these reflections. And when we transform this into the frequency domain, we get something like this down here. So the distance to these two objects, we see the object one here, the object two there. We can read out the distance directly from the frequency in which these kind of two peaks are presented, right? So in a sense, this is how the radar operates. We get the distance of the object. For all the reflections, we get a distance. And this is what you saw on the previous video. There was this cloud of points moving, right? So each of these points is actually exactly this happens there. So we send out a signal, we get a reflection back, and this the radar generates a point which is relative to the radar, is a point in a 3D space. Okay, so this is how that works. We get the distance. We can simply get the angle too, because we have not one antenna, we have multiple antennas next to each other. So basically by looking at the phase difference in which these reflections are received in the so there's a matter, if we look over multiple chirps, multiple reflections basically, and then we look how these distances change, we can actually then compute the velocity. Okay, this is what I wanted to have a brief explanation that we also kind of talk about the same topics. So this is how the radar operates, and this is how we can then perceive these, you saw these gestures, or basically first of all, these point clouds in these 3D space. Yeah, and that we can do gesture recognition. So here we have implemented this as a gesture recognition system building on these radars. So we have trained the system with a large number of gestures. So here you see these 21 gestures with which we have trained the system. And so then you want to see the confusion matrix here on the right side. So, and just as a brief explanation, so how to read this confusion matrix. So we have the actual gesture, which was performed. So let's say this gesture here was performed by the person. So this is gesture H, right? So this gesture is the actual gesture. And then in 98% of all cases, our algorithm actually predicted the correct gesture. So we can read here accuracy. So it basically means the diagonal should have the highest value, and see that most of the values are actually predicted at the close to 100% accuracy here. Okay, so that means we can have for even high number of gestures, we can really have kind of an interactive kind of environments where people can use the gestures to potentially, so we have seen this in the example, we can advance the slides and kind of control the slide set. But of course, we can have many more kind of interactive activities, interactive environments where this kind of gesture recognition is utilized. Okay, so there's one challenge in this. I didn't disclose right away. Typically, you know, of course, these point clouds, for instance, from LiDAR images from cars, right? I guess all of you have seen that. So the LiDAR is kind of, you send out the light, and basically there from the reflections, you can calculate very similar images, only that the LiDAR is typically much more fine grained. So we get so many points that you really can see environments from the reflections from these LiDAR images. For the point clouds, this is not actually possible. So we get in one chirp, which we send out, we get maybe 3 to 7 or 3 to 5 points. So one chirp, 3 to 5 points. So you can imagine that from that, when we just have one chirp, we cannot really understand the environment. So what we really need is that there's movement. And that helps us. So we see this here when we have a gesture. This is the kind of flapping, or what you call it, a gesture, like closing the hand in front of you. And we see that maybe for a couple of chirps, then we get these gestures here. And while the person is moving the hands, we see that the cloud point is moving, right? And so what we need to do, this is the collapsed point cloud actually for the same gestures. See, here's the torso of the person, the arms, right? And then the person is closing the arms. So this is what we see here for this gesture. And yeah, of course, if we collapse the points as it is here, then we can use point cloud processing mechanisms like for LiDAR systems, for instance. But as you see already, then the accuracy is not very high. So this wouldn't really help us. So what we need to do is to integrate temporal information. So basically, I mean, you can also imagine the order of things, of reflections will be a different order. So we really need to include, for activity recognition, we need to include the temporal domain. And yeah, that's something which at least a couple of years ago, the paper was 2020, was not common. So typically people haven't thought about having time domain for the, so basically 4-dimensional point cloud. So we not only have the X, Y, Z, but also the first dimension as time. Yeah, and what we did is that we integrated here an architecture for point cloud recognition. So this is an existing deep learning network. Basically, roughly you see this in green on the top right. So this is the existing network which we utilize. It was for point cloud recognition of these LiDAR point clouds. And you see that we integrated this here several times in our architecture. So this recognizes basically a static image of the point cloud. So we have a static image here, and then we have the next static image, and so on. So what we do, we have kind of a sequence of these point clouds, and then these are tied together with the LSTM, so with this LSTM type of layers to account for the temporal variations in the point cloud. Yeah, and you have seen the accuracy before, so we can be close to 100% accurate for the recognition with this type of system. The drawback, of course, is that this is far too big, right? So this can maybe your first implementation, then you need a small supercomputer to train this thing. So it's really huge in a sense. So you cannot you cannot really train it on your computer. It wouldn't be powerful enough, and you can definitely not run it on your mobile or embedded device, which you actually would like to have in smart environments. This can only be the first step. And so that basically, after showing that it generally works, the second step for us was to be, we further exploited the same domain, and we actually see this here in the middle. So the challenge was to have a much more efficient network. And what we did there's something called like a graph CNN. So it's a convolutional neural network for graph operations. And what we did is we transformed the point cloud into a graph. So the cloud of points basically of one chirp, you get a couple of points, and then basically to the next chirp, to the next couple of points, we use nearest neighbor approach to find the nearest points and connect them over time. So basically this generates between one chirp and the next chirp and the following chirp and so on, generate a graph in a 3D space, which basically can then be interpreted for the gestures. And this works actually quite well. So you see the accuracy down here. So we are, this Tesla model is the one we post there. And you see that we are basically close to, again, 100% accuracy, and we outperform. So this was the pantomime, which is already quite good. And there's a couple of other models. So we see that we outperform the state of the art at that time quite well. So it actually, even though it is much smaller, so you see the network here, so it's much smaller than the previous one and much more efficient for training. It can still be kind of more accurate than the state of the art. Okay, and that's maybe also something one should take home as a message. So it's you can always with the deep learning, you can just apply your deep learning on any data. It give you some results, right? You can be happy with that. But it's maybe not always the optimal solution. So it makes a lot of sense to consider the domain in which data is generated, maybe to optimize the network or to build a new one, which is then more efficient and even maybe more accurate than the previous network. Yeah, and just to demonstrate how kind of efficient that was, so we used the Raspberry Pi 4. So it was actually a small computer, if you want, but still we could run the model completely on the Raspberry Pi 4, which was for some of the other models even not possible, right? Because they just need too much resources, especially storage resources and RAM to actually fit the model in. And this was well possible for the Tesla model, but for some of the other models, even not possible. But we are still even much more efficient. We reach quite a good accuracy compared to the others. Yeah, you see this actually here. So we have here a little bit the size. So you see the pantomime is really huge. So since we included this point net plus several times into the pantomime, but yeah, so still the Tesla is much more efficient than the other nets. Okay, so that's just briefly on this point cloud type of recognition, and I will talk about a couple of topics which I think are relevant at the moment and which I feel they are still kind of a research challenges and people are working on these at the moment. So that is, for instance, the multi-person recognition. So it's we have a lot of work in recent years on single-person recognition. So it's just one person in the environment. There's not much interference. So it's actually an easy case in a sense. But then what is much more challenging is that when there's 2 persons, 3 persons, 5 persons, 7 persons, so can you not only count them, let's say, okay, there's a crowd of persons, but can you actually distinguish each individual, like individually or separately, and know where they are and what gestures or activities they are performing at the point in time. And yeah, for this, we show that with the same architecture, it's actually possible. So you see the setup down here. We have multiple radars in an environment which was actually a little bit larger. I think we have 5 times 5 meters as for this environment. And then we have people walking kind of in the center of this environment, right? And they're walking and also, okay, this is not in the slide, but we show that they can also perform gestures and we can still recognize the gestures. So they were walking around, and basically when you collapse the data from all the radars. So this on the right side, this is what you get. So this is kind of it's a mess if you want. So this is the data from all the person. The time is going here in the Z direction from bottom to top. And so one dimension we actually ignored here because we only want to know the X, Y, and not the Z dimension. So the Z is here the time. And you see that how people, you can actually see that something is going around here, but obviously you cannot distinguish individuals from this data. But then, so what we implied here, we use the clustering algorithms for clustering the points into separate point clouds from each other. And then this is possible, at least in the current approach, we can separate up to 7 people at the same time. And the good thing is you get data basically like this, right? You get the movement data of the person merged. So you basically see where they move in time. But what you can also see, because it's still a point cloud, we can also, that's not on the slide here, but we show that we can also recognize gestures. So if the person is moving and performing gestures, then we can still interpret this from the point cloud data. So that is, to my information, very difficult for a lot of other technologies. So that you can have both the location and the gestures accurately in such kind of an environment. And of course, you can say that the camera might do this also, but also the camera has limitations. So there might be shadowing effects that you kind of cannot see all the people at the same time. Yeah, so there's obviously to any sensing technology, there are some limitations. For the radar, it works quite okay at the moment. Of course, we have also limitations of 7. We couldn't do more than 7 at the moment, but it also depends, of course, on the size of the space where you want to do the sensing. Okay, and I go through a couple of topics, right? So this was the first topic where I think if somebody of the audience is also interested in this topic, I think that is something with more publications and what is coming in the near future. Yeah, another very relevant topic and often discussed, you might know this, many of you, this is this joint communication and sensing. So the idea is that in communication technology, there's the thought that we don't only want to communicate, but you also want to do some sensing, right? So can we actually use these communication networks? Let's say, can we use a 5G, 6G network and a Wi-Fi network? Can we use it also for sensing, right? Can it help us to know the situation in some environment? Can we do interactive systems like a free space gestures by using these? They're already installed systems, right? It would be quite high potential in the sense that you have the installation already. So it's kind of a zero cost. In the best case, you would need a software update, right? So then suddenly your device becomes sensing capable. So that also goes into the direction which I mentioned in the beginning. So really, if you want to think about services to imply to deploy in these ambient intelligent spaces, then you need, in the best case, an infrastructure which is installed already everywhere. Like, for instance, the 5G network, the Wi-Fi network, so that somebody could buy your service and install it in their home router or in their home network, and just employ this as a service at home for, let's say, smart interaction. Yeah, and so one idea here which we propose, of course, there's many others, is there's a technology called cycling in the 6G. You might have heard of that. So the idea is that the device, which can be your mobile phone, for instance, or I call it a radar. We basically turn the mobile phone into a radar. So the device can actually request resources from the network, right? So the device requests resources. Okay, I need resources in the next, I don't know, couple of minutes. And typically, it's designed for point-to-point network connection, right? Maybe to transmit data to the other device. But in our case, now it's not used for communication, but actually for sensing. So the idea is that we utilize this the resources which are granted then, and that is new. That is not in the standard at the moment. But I think since the resources are granted, the proposal is that we can actually use them for sensing the channel. And so then, okay, sorry, this is another issue we can talk about in a second. And then basically we can do sensing in these kind of environments, and it introduces something which I have on the right side. So if you have these situations, then typically in any kind of these sensing scenarios, you typically have this 0 degree, a very simple or simple case where you do all the training with one device, where your subject is facing the device and you perform the gestures, you train the device and so on. And it works very well. You have seen that with the 90% or 98% accuracy. We have seen that before. But in a real environment, when you suddenly have your phone and the phone becomes your sensor and you just place it somewhere, let's say you place it here, and then, I mean, you not necessarily perform your gestures always directly towards the phone, right? It might be that you perform the gesture in this direction, but because that's maybe where your service kind of, you want to interact with the light or with the whatever, with the blinds in your apartment, and just the phone is at your back a little bit. Still should still work, but you might be able to imagine that if you perform the gesture in a different angle or a different direction, for the sensing system, it looks completely different, right? It's just not the same gesture. So that's kind of a challenge which we have been addressing. You can see this here also, like this bluish one is the existing work in the literature. So we see that when we train the system with all of the data, right, in all angles, and we basically just take away one, maybe we just take away this one, but we have trained it with all other angles, then the accuracy is still quite high. But as we start taking away more and more antennas from the training, we see that the accuracy of those systems gradually decreases until it becomes basically unusable. So if we have this situation really that we want to train it only in one direction, and then we want to apply the system arbitrarily in a natural environment, then kind of the standard systems here, basically these systems, they typically don't work. But what you can do, you can try to have a rotation invariant representation of the data, which is so we're working this for quite a while. It's more difficult than you would think. But you can also have some other things. So we have tried this with some pooling, attention pooling and vote pooling approaches. You can also try to actually track the orientation by analyzing the gesture you are looking at. So this is not perfect, but you see that with these kind of approaches, then the accuracy still stays high for quite a while. So we don't have to use so much training data from all possible angles, but we can actually mitigate this kind of directionality issue to some extent. Yeah, I think this is still an open issue, and still there's quite some research going on in this direction. Yeah, but you can do something as indicated here when you prepare your algorithm in a proper way. Okay, and so we have now talked a lot about systems installed in base stations, in 6G and Wi-Fi base stations. So kind of you always have a powered system. There's always like energy for power them. You can have metal antennas. You have really powerful processor in there. But another direction you might want to think is that what if we go the other way? So what if we make the device very, very simple, like thinking of IoT, and we want to integrate it actually in some environments, as we have seen beforehand. So then can we actually have even printed devices? Can we integrate, like indicated here, can we integrate these type of antennas into furniture, into maybe the walls? Can we have it into the tapestry? Right? So for instance, can it be in the, let's say, can it be into clothing? So could you have some, let's say, conductive textile where you integrate an antenna and maybe some small logic circuit and actually perform some sensing? So that's some work which is currently ongoing. I think which is yeah. Let's see. I hope that we will see some very positive results from there in the near future. So we have tried this a little bit to investigate, okay, is this actually feasible? So what we did is that this is the FarSense. You can actually buy this. It's an RF monitor, if you want. It's battery free. It's like an RFID. It has an RFID. So basically, you cannot see it, but here's basically an antenna in here. It's the whole thing is basically an antenna. There's a small chip here. The basically RFID type of chip. It's not reflecting the signal, but what it does, there's an LED, and when there's the RF energy, so which is received is higher via this antenna, then the LED will light up, right? So it basically can light up. Right? So then we use this And what we did is we had these grids here. You see, we have a grid of 9 sensors, which we integrated. See on the right side, we integrated this, in this case, not in the furniture, but under the table, or we attached them here to the body of a person, and the person was performing some gestures. And so what we can see is that for kind of a small, simple activities like here is like rising the arm, lowering the arm, and so kind of these movements, these arm movements, we can easily detect with these kind of simple sensors at an okay accuracy. And the same is like we have here. We perform some activities. You see them here over on top of the table where the sensor board was underneath. So again, we get quite a reasonable accuracy. So I think that's, in my opinion, super interesting, that moving towards a scenario where we can have really cheap devices, maybe battery-free devices, which are then able to perform the sensing in these kind of embedded intelligence scenarios. So we have the intelligence that is sensing in the scenario, and this by really cheap installation. So because another thing is, and especially battery-free installations would be very helpful, because you don't want to install a lot of devices in your smart home, and then every now and then you have to change the batteries. So that just doesn't fly. So it has to be something which is really sustainable over a long time. Yeah, and this project I wanted to point at, which actually targets this. This is the Sustain project, where I have to say, so Alto is one partner, but Yildiz University is also another partner, and some others. And what we are building there is these kind of devices. You can see them here on the left side, where then this is really now our own devices, our own design and printed, where we try to use the RF signal for sensing on the device. So the idea is to have a device, a single device, which is kind of autonomous, and which can form a group of devices together towards this sensing of the intelligent environments. And yeah, so there's other partners. So the idea, so questions here are both on the sensing, of course, on the energy efficiency, so kind of the energy harvesting from radio, but also from other sources. It's about the communication between the devices, so how to connect all these together, but also it's about the algorithms, so how to, on the one hand, interpret these stimuli from the different devices for gesture recognition, for instance, or for activity recognition, but also about the security. So how to make this secure, because actually now you have very tiny devices. So how on these tiny devices we can protect kind of the privacy of spaces, right? So we don't want that somebody outside of the room can just observe which kind of activities are performed inside the room. Because of these devices are kind of sharing information with each other wireless. Okay, so that's kind of a challenge we have, or kind of problems we are looking at the moment. And yeah, just to motivate, so kind of how else we could utilize this, and this is also part of the Sustain project. So we also think about attaching these sensors, integrate them into textile, into clothing, and we have currently demonstrated that it's possible. Let's say if we have 2 of these sensor tags, let's say on 2 different sides of the body, so let's say 2 different arms, then it's possible with some tricks that you actually change the face profile on the one sensor in a different way than on the other sensor, and then you can distinguish the 2 different hands, basically, and that's something which is actually will help us. So it's kind of a point, how you call it, a marker-based system. So you know this from image or from video, that people bring out markers at the subject, and then when the subject moves and the marker moves, we can actually have basically how is it, a skeleton picture of the moving object, right? And we are moving in this direction now, basically with the Wi-Fi. Or not Wi-Fi, with the RFID tags, that we bring them out as a marker on the person's body, and we can distinguish the different kind of Wi-Fi tags, and thereby basically have a marker-based system to improve the recognition. Okay, that's for the Sustain, but there's of course one thing that we also always have in mind. So I will be talking about systems which we can install, which are basically ubiquitously installed because we say they can be integrated into 6G, into Wi-Fi, and kind of there's this big brother situation, which of course we should be afraid of, we should take care of. So another aspect is, well, if we have these systems, if all of your kind of Wi-Fi capable devices would soon potentially be a sensor, then of course the question is, would this be accepted by the society? It feel like a big brother system which is kind of monitoring all your activities all the time. So there's some risk here. And so for this we have another project running at the moment. It's called Holden Project, where we think of solutions, how to actually, it would more like democratize the technology. So kind of the idea is to open an interface to, and that's kind of new, I would say, compared to existing systems where you have your own device, only you have access there, right? But the idea is that in these kind of smart environment systems, that's kind of a device where multiple people utilize that environment. So we should give access, and we should give an interface for multiple people to interact with the environment. Then towards privacy, there are kind of thoughts that we can, how can we actually enable personalized privacy and even personalized interaction or interface to everybody in the environment. They could basically control and say, okay, I don't want to be tracked. And then of course there must be ways in the system to let's say to ignore the data from that person, right? So one thing you could think, if you imagine the point clouds, which I've seen before, at the device level, you can actually, before you give out the point cloud to any machine learning system, you can actually modify it, right? So why don't we add some new points there? Why don't we add some noise in the points? Why don't we take points away? So I think we are quite in a good position there to actually control the privacy aspects. To really, if we say, okay, here in this room, in this space, it shouldn't be possible to distinguish people, right? In another space, it might be okay. So we can just add some noise to the points before we give them out. So any kind of machine learning algorithm would basically not have a chance to have very accurate recognition, but would be limited to data which we give out. Okay, and so this, I would say, closes the loop a little bit. So we have talked about, first of all, the idea. So we would like to have environments where we can install services, right? There could be a service provider programming for these kind of spaces. We have talked a little bit about the technology for contactless sensing, and what we are using in the group is a lot of RF sensing, which has a high potential, I think, because it can be integrated in already existing environments where we have the Wi-Fi and we have the 5G already, and it gives a lot of opportunity. We have seen the sensing accuracy is quite high, also for the gesture recognition with many gestures, with many people, and so on, and of course, we can even scale it down to this kind of energy gentle devices, like small devices, which are can potentially printed and integrated into environments. And also lately, lastly, now the aspects about the privacy. So basically, there are privacy issues, of course, and but I think I'm positive that we can actually address them in a technological way to solve these privacy issues. Yeah, and this brings me to the end of the presentation. So thank you very much.
Thank you very much, Stefan. You gave us very valuable and up-to-date information. So these information are very new for our listeners, maybe, because most of the listeners are students from electronics and communication engineering. So the information that you gave us are really very valuable.
There's we are typically very open to any kind of, if there's a student interested in these topics. So can you hear me? It says the internet connection is unstable.
A little bit, yes, we have a little bit internet problem. But
oh, okay. Sorry.
We hear you
okay,
now. It's okay.
I'm sorry for this. Yeah, so I just wanted to say that if there's any questions, of course, please reach out. Very happy to answer any questions. And in principle, we have now a collaboration with Yildiz, so we can also think about other type of even exchanges if there's interest. just saying.
That's a good comment, because I will write you about this subject an email. We want to collaborate with you with another subject, but I will write you the details. But you pointed a good subject. Thank you. I want to ask the listeners if they have any question. Just wait for the questions. Maybe they can ask using their microphones, or maybe they can ask in the chat box. I don't know.
Sure. Everything good. I just open the chat box, but the microphone is also good. Sometimes it's more direct to direct.
Yes. But I can ask a question firstly. Okay, you gave us information about contactless gesture recognition, and you said that we can also solve the problems using multiple people. But I have to ask, what happens if some things go bad? I mean, what happens if there is occlusion between people, one with another?
Yeah, that's it's also an issue. Yeah, it's true. So I go back to this here. Yeah, it can happen, of course. Yeah, it's true. Like, let's say we have this red person here, and then maybe there's another person walking on the other side. So this sensor would basically see, right? It get the reflection from this red person, but then some data would be missing here on the other side. So what helps us in this scenario was that we have multiple sensors. So you can basically, if you combine the data, you can account for this occlusion. But it is true, right? So that is similar to video. It is still an issue. So I mean, you might know there's wall applications for Wi-Fi sensing, but it's not. You cannot really go through people and or through metallic objects or the thick walls. So in principle, you have to account for this on the algorithm side.
Do you think using stereo cameras and using both LiDAR or radar and combining all the features can be a solution to this problem?
Yeah, definitely. So if you have more sensors, I'm quite sure it helps. So if you have cameras on top of that, the question is always I think it depends on the application, right? If you have an industrial use case, I think then it makes a lot of sense to integrate cameras because you get maybe more information, right? But maybe you have an elderly care use case where you like to monitor in the home environment. So maybe you don't want to have the camera in your living room, just could be. So then the Wi-Fi sensing is still kind of a good alternative, providing a good accuracy, but it's not so privacy intrusive.
Exactly. For example, for autonomous driving problem, you can use both LiDAR and cameras, and we can combine all the features.
Yeah, sure. Yeah, exactly. Yeah, exactly as you said. Yes, that's true.
Yes, I agree with you. Thank you for the answer, but I want to ask again if there's another question or not. If there's not, we will all thank you for joining us here in the night, here in Turkey, but not in Finland, I think.
Yeah, we should soon have it in person, right? Maybe we have sometimes a project meeting in Turkey, but let's see. Maybe next time.
Of course. Thank you, Stefan.
Yeah, I also wanted to thank you again. Thanks for the opportunity.
Thank you. See you then. Bye.
Yeah, see you. Bye.
Goodbye.
Thank you very much.
Thank you.